Okay, great. So thanks for joining me. Hello, everybody. I'm Rafael, and I'm going to give an introduction to Java performance today. I'll just share my screens right away. So here we go. Right, so before I start, this is an introductory talk. I'm not going to go into machine code assembly here or anything that people often are afraid of. This is really intended for every Java developer who's wondering about how to write performant Java code. And during the session, if you have questions, please come up with them while we go. I'm trying to cover as much as possible, but it's really an endless topic anyway, so I rather go through a few topics and go through them in detail such that everybody understands them rather than covering a lot and nobody gets it, right? So, and if you have a question, probably someone else is wondering about the same thing. So please just ask, and I'm sure Simon will pick it up and interfere my talk, right? Okay, but before we start, just a quick commercial. I am writing a library called ByteBuddy, and it's currently awarded, or like not awarded, but nominated for a JUX Innovation Award. So everybody who hasn't voted and feels like voting, please go to juxlondon.com, JUX Awards, and I would, of course, be pleased if you vote for ByteBuddy there. Also, check out the library. It's a code generation tool. It's used by a lot of libraries and also end developers for writing Java agents and the like. One of these tools, by the way, is Mockito, which is the other one I want to advertise for here. We are currently working on releasing Mockito version 2. We have changed quite a lot, but the migration should be pretty smooth. So we didn't change much of the public API, but with Mockito 2, we are releasing a new release candidate tomorrow where you can actually, for the first time, mock final types and methods if you want to. So please check this out and give us some feedback. We didn't get so much testing material yet. So we, of course, do hope it works, but in the end, we need to verify it on the release candidates before we can publish a final version. Okay, great. So I'll get started. And a first disclaimer, especially since these things are recorded, right? And you might watch this on a video a long time in the future. Now it's September 2016, right? Once we talk about Java performance, things change a lot over the time, right? So if you find performance advice for the JVM, which was valid for Java 4, Java 5, this is not necessarily true today anymore if you run it on a Java 8 machine. So unfortunately, or fortunately, because Java still evolves, you have to always be very careful. What I'm talking today is valid for Hotspot mostly, so the OpenJDK VM, and for Java 8, and will probably mostly be valid for Java 9, but things, as I said, change. So be a bit careful also if you Google, if you apply these things in a couple of years, you have to stay up to date here. All right. So what I want to talk today about is this chain. And we as developers, we tend to not like to think about anything beyond our program, right? So that's the big promise of Java. You write it once and you run it anywhere. So we write a Java program and then we do compile it. We do compile it using Java C. So we get source code and we put it into Java C and we get bytecode. And this bytecode, Java bytecode, is still pretty high level. It's still pretty similar to the Java program that we originally wrote. And this might be also a Scala program or a Clojure program. All these things compile down to bytecode. And then we give it to the virtual machine, and the virtual machine runs it. And we typically do not really care much about how this program is ran. But once we have some high performance constraints, actually, it is pretty important to understand a bit, at least, what the virtual machine is doing and how it works, because this idea that we can just write any code, feed it to a virtual machine, and then there will be super efficient machine code coming out of it, this is not true. Because this is actually what's happening. The Java virtual machine takes our bytecode at runtime, it basically looks at our code while it runs, and then it translates it to machine code. And this machine code is then fed to the processor, because the processor doesn't understand anything else than these instructions, right? And that's also why the Java virtual machine works on different platforms. It's because the virtual machine translates it to different machine code depending on the platform you're running on. So you will get a different program on Linux than on Windows, and you will get a different program on Intel than you will get on ARM, right? So I'm trying today to break a bit through this Java C barrier and look into the transformations that are applied at runtime of a Java program and how the Java virtual machine looks at our program and what in a way makes a fast program. But as I said, without looking at actual machine code, I am trying to do it high level and in a way as if the Java virtual machine was transforming our source code into something else. All right. So Hotspot, the virtual machine, actually is a very dynamic system. Our code within Hotspot is tracked at the method level. So every method within a Java program is one unit of potential optimization. And every method is run by different basically runtimes in the virtual machine, depending on how important the Java virtual machine regards this method. So if you have a method foo, the runtime of this method foo depends very much on the importance, or in a way the hotness of the method. And that's where the name actually comes from. Hotspot tries to find important methods, and then it spends some time to optimize those methods instead of optimizing our entire program, which is something like a C compiler would do, but not at runtime, but while building the program. And obviously the reason for Hotspot to identify important methods is that it is happening at runtime. So there's always a trade-off for virtual machine to basically spend time executing user code or spend time making that code fast. While you make a program fast, you cannot execute it. So you burn cycles for the wrong thing, right? So every method in Hotspot, in a way, starts out in the interpreter, which is like a machine code templating engine. So every instruction basically has a machine code template, which is run once the instruction is encountered. And then the program is actually run as you write it, instruction by instruction. This is also called level 0 in Hotspot. So from level 0, you can evolve to the C1 and the former client compiler. So what Hotspot does is it has different compilers, a C1 and a C2 compiler, which apply different levels of optimizations. And the problem here is that you can make a method very fast, but as I said before, this takes some time. And this time that you spend optimizing the program, you don't have time to execute the program. So you have to trade off, and sometimes a method might not need it to be optimized that much, and then you can run it in C1. What Hotspot also does is that it looks at your code while it's running, and it creates a so-called profile of your code. A profile meaning to see what execution path do you take through a method. Do you maybe have an if statement and always executes to true, so the else statement is never executed? Maybe you have a virtual method that is not actually virtual, but you always call it in the same instance. And then based on this profile, different optimizations might be applied depending on what was observed before. So C1 has basically 3 states, which are called level 1 to 3, where basic optimizations are applied, and depending on the profiling level, certain information is collected. And there's different levels, like simple profiling, advanced profiling. And as a matter of fact, level 1 typically is faster than level 2 and 3 because no profiling is done. But I'll explain more about this later. And then finally, the server compiler is using this profile to apply an optimization. So this is level 4. So when you run a Java program, it typically starts out slow. All of your methods start in level 0. And then over time, through execution, the Java virtual machine has learned a lot about your program, optimizes it based on this information. And then after a few minutes of runtime, your Java program is fast for the first time. And that's a significant difference to any C programming, right? So C program is basically optimized from the beginning, but it is only optimized for a static state. A Java program typically starts out in a non-optimized state, but it then evolves into something that might even be faster than a C program that would express the similar logic, because the Java virtual machine can make assumptions about your code that might not hold true before the program is run. So, and the journey of a method, as I said, starts at level 0, is typically going to C1 with advanced profiling, and then transitioning to level 4 at some point once it is executed many times and the Java virtual machine has learned a lot about your method. So furthermore, another scenario is, of course, that you start out on level 0 and you only go to level 2. And what is that for? And the problem is that advanced profiling, as I mentioned, takes some time. You have to collect additional information. When you collect this information, you're not executing user code. Your program might run faster, slower. So if the Java virtual machine recognizes that it currently is spending quite a lot of time profiling already, it might not activate advanced profiling for a method right away, but just collect some basic information and then later go over to advanced profiling before compiling it to C2. And the same might be true that it starts out with machine code templating, profiles it a lot, but then realizes, okay, you know what, this is a trivial method. I don't even need to optimize it. I fall back to level 1. And this scenario is typically true for like getters or setters. Methods that are just too simple to spend actual optimization power upon, right? So, and this is these 3 life cycles are the typical life cycles of a Java method throughout an execution. And given the system here, it is of course very difficult to reason about performance in a Java program because you don't really know, or you can know, but typically you don't know where a method is. So if you write, for example, a benchmark, you might measure it first in level 0, then in level 3, and then level 4. And you also might measure the time it takes to compile the method in between. While typically you're only interested in the steady state performance of level 4. But I'll get to that later in my talk, how you can actually measure runtime. But this is the general setup. This is the states your program walks through while you execute code. Okay, so given the system, I want to go through some optimizations that the Java virtual machine applies, and I'll showcase this profiling mechanism that I mentioned. And what I want to go through, and if you just get this one part of this talk, so if this is the only thing, remember, you already have won a lot. And this is understanding how call sites work, right? So call sites are basically these things here. Anytime you call a method, but the specific location where you call a method, that's called a call site. And one thing that is very different in Java than to any previous languages, like for example C++ or even C#, they don't have virtual method dispatch as a default. So virtual method dispatch means that if we call bar on foo here, we don't really know what method we call, because foo could override, a subclass of foo could override bar, and then only at runtime we will find out what method we actually invoke. And this is actually quite problematic for an optimizing compiler. And I'll just show why. So how can a virtual machine or any program know what method to invoke when calling bar here? So there's an indirection, right? All such languages have something that is called a virtual method table, or also typically called vtable. And the vtable is just a table with all methods that are invoked virtually on foo here. So we have hash code, equals, toString, and a couple of other methods that are declared by object and which are not overridden here. And all of these methods basically point to a machine code address. And the machine code address is where the program is currently storing the method, this system out println, right? And what we have to do if we encounter a bar, we basically have to find the virtual method table for this specific class, which is now foo. Then we find the machine code address of the method here and see that it points to system out println hello. If there was another class sub which overrode bar, then we would have another implementation here, right? And then this class's virtual method table would also have an index 8 with method bar, which points to another machine code address. And this is how the virtual machine then finds out to print whoops instead of hello. And one very nice thing about single inheritance programming languages is that you actually can guarantee that the method is always has the same index. That's not true for itables, for interfaces, where you don't have a strict overriding hierarchy, but it's basically the same idea. Yeah, and basically every time you would invoke a method, you would need to basically first find out what class we have for the instance. Then you would have to find the method table for this instance, and then you would find the address for foo, for bar, I mean, in this case for the method that we're executing. And that doesn't sound like much, right? That's just 3 things we have to do. But you should know that this is 3 things we have to do every time we call a method. And that's basically what we do during a Java program's execution, is we execute methods all of the time. And adding just 3 indirections makes methods calls 3 times slower in the worst case, compared to just executing 1 thing in order to do it, right? And this is why this is such a critical problem. This is why many languages avoid virtual method dispatch. That's why in C++, for example, you typically don't declare methods virtual if they are critical. But overriding methods is, of course, an important point in object-oriented programming. So you want to make this faster, right? So, and one way to make this faster would, of course, be to add a cache. And basically you say, okay, we probably this method has a good chance that this is foo. So we just retain a cache at the call side where we store the address of the bar method we want to execute. And I'll just say it right now, Java isn't doing that, but Smalltalk was doing it. The language where Java took a lot of inspiration from had caches. And once we came to a call side, we could just find this cached link. So if foo was an actual instance of foo and not a subclass, we could just look the address up in the cache and jump right to executing bar, right? So, but as I said, this is not what Java's doing. Java's doing something even more aggressive. Java just observes, or the Java virtual machine rather, or hotspot in particular, it just observes, okay, let's just assume that foo is never subclass in our program. And this is something we might even be able to prove temporarily when we say, okay, currently there doesn't even exist a subclass for foo. Then we just assume that this value is always an actual instance of foo and that we always will need to print hello. And this goto is then basically just 1 indirection. So this is why profiling is such an important part, right? So if you remember back when I showed you these level 0 to level 4 compilation stages, during level 0 to level 3, or rather level 2 and 3, the Java virtual machine will have profiled the call side to and check for its type. So it will remember, okay, I called this bar method 10,000 times, for example, and the instance that was delivered was always a direct instance of class foo and never a subclass's instance. So I'm just assuming that this is always true from now on. Maybe this is the steady state of the program. Maybe there was a setup switch added in the configuration of the program that leads to the fact that this is always foo and never a subclass. Maybe I need to enable a feature that doesn't matter for us now, right here. And then we can do this like here. And in the case that this is no longer true, the virtual machine adds an assertion in a way where if this is ever not true, it basically breaks the program and just rethinks how to do this differently. It probably will just fall back to level 0 and restart interpreting, which then is an expensive operation once this assumption is not true anymore. But as long as it holds, this is basically as fast as the code can get. And this is basically already a first real-life performance advice. If you have call sites, try to keep them constant. Don't try to add unnecessary overrides. I'm not saying that you should avoid overrides at all, but if you can solve something more elegantly without overriding a method call, then there's a good chance that your program will execute faster, because every time you call a method, it will just be invoked directly instead of having this indirection via a method table. Right, so And there's different states of a call site as well. And I just want to go through these. And the best one is a monomorphic call site. And a monomorphic call site is a call site with only one ever occurring type. And that's what we just saw right now in the example. Foo is never subclassed, so it's monomorphic. And actually 90% of all methods in a typical Java program are monomorphic. Because think of getters and setters again. These methods are typically never overridden. And then the Java virtual machine will just say, okay, I observed this getter call so many times, I will just inline the code of this getter, right? And then it will have the same performance and the actual same performance as if you access the field directly. So, and that's why there's no performance overhead to getters and setters. If there wasn't a performance overhead, this would be something that people would tell you about, right? You would hear all of the time, don't write getters and setters in a performance critical environment because they have overhead. The truth is they don't, and it's because of this assumption that the JVM can make. They will never be overridden, right? All right, so monomorphic isn't the only good state of a call site. Bimorphic is also still quite okay. Bimorphic still means that the Java virtual machine will remember the actual machine code address of the code to execute, even if one interface, for example, has two implementations that occur at a specific call site. And an example would be a collection, for example. This is where this typically applies. You have a collection, which can be an array list or a linked list, and both types occur regularly, but since it's only these two ever types, you can still remember the direct machine code address at the call site and jump there from there without going to a method table. A polymorphic call site doesn't exist in Java. Everything beyond bimorphic is already megamorphic, where you will end up with this vtable lookup. So if I do performance optimizations on a client program, for example, this is something I often go for first. It's vtable lookups and try to avoid erratic call behavior. And sometimes this can actually trigger quite a lot of optimizations, and I'll show in a second how it's not only about avoiding the vtable lookup, but also about the optimizations you break by requiring a vtable lookup. Finally, for vtable lookup, there's actually still an optimization applicable if you have a dominant target. That means that 90% of the time, a call site is done on a specific type and 10% of the times on other types. Then the VM will still optimize for this dominant class, but not for the other class where there's always done a vtable lookup. And yeah, I already said that the VM makes assumptions, right? So we might start out with a vtable lookup, and then after a while, the VM says, okay, you know what? I'll turn this into a direct link because this is actually monomorphic. For the last 10 minutes, I only ever observed a specific type. I'll go there. And then once this assumption doesn't hold anymore, the virtual machine might de-optimize this again. This is something legitimate, right? It'd say, okay, this assumption that I made was true now for 2 or 3 hours, but the program state has apparently changed, and this is not true anymore. So I have to go back and see if I find a better profile, which I can optimize upon again. And this is how your system is constantly moving, and it's actually quite important for especially high-performance system. Let's say you have a trading application, right? And markets open in London, right? And when markets open, you have suddenly a significant higher rate of orders because the official ordering systems are open again. And then the JVM in the worst case might say, okay, you know what? I need to change the code. I need to stop running fast code, but I have to make the code fast again. And then especially when the market is hot right at opening, your VM spends more time on these optimizations. So then you have to be very careful how you develop a Java program. And that's why also some people say like real-time systems are difficult also with regards to garbage collection, because these things you don't control really. This is something that VM does for you. And you can still write the system in Java and it actually works quite well, but you really need to know the machine you're running upon, and you need to know the virtual machine you're executing in order to anticipate these changes and to maybe trick the compiler into doing something particular. So I already mentioned that virtual method dispatch is something you want to avoid, not only because of the virtual dispatch itself, but also for the consequences. And the reason for that is inlining. And inlining basically means that the VM copy and pastes your code to the invocation side. So instead of just going to the method address, the VM might just take the code and copy paste it into the do something method. So what happened here is that we avoid the method call altogether, but we have duplicated this code, system out println, and have it right in our method. And that's, of course, a further optimization that we profit from, right? And this is not stopping here. Once you inline code, let's say you have a method foo that calls a method bar that calls a method cooks. Once you inline bar, you might also be able to inline cooks in a later step. So this cascades. And once you have a virtual method dispatch in between, this inlining doesn't work anymore. So you might stop a whole chain of events. And this is why sometimes small changes can have big effects in performance. By that, I mean like batch jobs running 3 times as slow or 3 times as fast, only because you have optimized something that had a huge effect on the virtual machine's optimization without you even realizing that. And that's actually not so uncommon at all. Right, so this is the Uber optimization. I always have these texts. You can find the slides online if you want to read them up. I know these topics sometimes need some digestion. Then you can find them and hopefully understand from the texts what I was saying on the slide. So one example for this call side pollution, I'd like to. Yeah, please.
Yeah, so with the monomorphic, bimorphic, etc. So that means that every time a call is being made, it has to ask a question. It has to go through an if, right? Is that type the type we think it is?
You mean the assert statement here, or?
So even if it said, all right, for the last 10 minutes, every single call to this method, that type has been the same type every single time, it still has to make an if, though, right?
It's not a real if. It's more, see, the type of every object is stored in that object's header. Accessing this type information is very cheap. So basically, it can just check if this hash value of the type is the one we expected, and if not, then we basically interrupt the program. So it's more than if. What you do is you basically you align all the caches, all information is prefetched with the assumption that the type is the right type, that the one that we expect. But once it's not true anymore, we just fall out the program. We basically make an interrupt of the current execution chain. We probably flush the caches. We rebuild our actual Java program and fall back to the interpreter. So this assertion is more than if. It's I know I actually had this question before once when I gave this talk. It feels like it, but it's the assertion is pretty cheap unless it fails. That's what the idea is.
Is that the equivalent of throwing an exception then, or is
not really, but in a way, yeah. I think it's fair to think about it like that because in a way we fall back a few frames in the method stack, typically, but it's cheaper than an exception. It's basically just a check. It's I think it's called an uncommon trap in this context. So. We say this is not supposed to happen, but if it happens, just interrupt the control flow that we go through now, or the execution chain we go through now, and do something else. But hopefully it doesn't. If we always fell into these traps, a Java program would become incredibly slow, much more slow than if we actually had an if-else. So in a way, it's a trade-off, saying, okay, we bias our program in the direction that this assertion never fails.
Thank you.
Yeah, you're welcome. Thanks for asking. Right. So an example of such call side pollution that I actually have seen many times in practice is collections and this constraint, this system here, so-called double brace initialization. So let's say we had a list and we called the size method on it. And the list was either array list or linked list every time we called size, right? Then we have a bimorphic call side. But then at some point in the program, someone creates an array list with this so-called double brace initialization, which is basically just creating a subclass of ArrayList and adds a constructor in which add foo and add bar is called. And people like this because it feels more fluent, right? You can inline this statement. But what you actually do is you create a new type. And this is already a bad idea because you keep a reference to the outer instance if it is not called within a static context. And then you create a memory leak in the worst case. But what you also do is you create a third type. And if this type appears at the size method invocation, then you have suddenly a megamorphic call site. And for the size method call, it might not be so bad because there's not so much to inline in there, but it's still a potential performance threat. And I had this problem especially with, also with Scala, it's a problem. Scala has specialized collection for 1 element, 2 elements, 0 elements, and even Java has like the 0 and 1 elements specific collection. I once had a case where I simply removed these specialized collections which require less memory, but still pollute our call sites with a third type. And this is what I would say like an unnecessary override. And override doesn't mean that we have to override size. It just means that we add a third type into our profile, which then and a machine isn't smart, right? A machine isn't intelligent. It's just following a protocol, and the protocol says more than 2 types at a call site means I don't optimize it the same way anymore. So this is the problem here, right? And that's why you want to avoid this, right? So given all this information, let's look at a typical method call from a logging framework. And logging frameworks have log methods, which typically are accepting a var args argument. And then let's say we want to print all these arguments. This is a very simple log method that we wouldn't run anywhere, but it's just an example, right? So what we do here is we print log, and then we iterate over all the arguments, and we print toString. And we basically know already that if we call this from many places in our program, this will be very megamorphic because argument can literally be anything, any type that exists in our Java program. Object is the supertype of all types, so this can supply anything. And then this would run slow. But let's say we call this log method here, and with a string, with an integer, and with an object, which makes 3 types, meaning that the call site toString here would be megamorphic in the end, which would mean that we have this additional lookup cost and have all this megamorphism that we have to deal with. So, but since this log method is static, it is inlineable very trivially, right? So we can copy it. And once we copy it, we can apply new optimizations. And that's basically the reason why inlining is so important. By inlining, you specialize your code implicitly, right? This loop we can just unroll, which is an optimization, and end up with that code. So this is equivalent to the above code. And this is something the virtual machine will figure out for you. And now, instead of having 1 megamorphic call site, we have suddenly 3 monomorphic call sites, which is good because now if this do something method is executed a lot, we can just basically, again, inline these toString method calls and optimize the program altogether. This is something that virtual machine will do, but it's only capable of doing so but because the log method was static in this case and easy to inline. If the log method wouldn't be static, but would be virtual, and wouldn't be basically inlineable and for some reason, then we really would have a problem here. Then this log method would really become a bottleneck to basically handle all of these var arg dispatches, because then suddenly you don't know how long your loop is going to be anymore. You're not going to know what type of arguments you're going to accept, and then you have to pay the costs for not having this. And this is why homemade logging frameworks, I've seen many of them throughout my work as a consultant, and they typically are always a huge performance threat. So be careful once you call or write such generic. Also, if you write utilities, right? If you write utilities that you use throughout all of your application, make sure that these utilities are inlineable. Otherwise, you end up with this problem that we have shown here, right? Okay, and as a matter of fact, all programs are typed. So let's just have a quick look at JavaScript or V8, the engine running node. So also these runtimes optimize based on type systems. So let's say we have a variable foo and we define two properties, x and y. What V8 will do in order to optimize, and V8 optimizes not so unsimilarly as Hotspot, it will create a so-called hidden class for every object. And the hidden class is made up of its properties and the actual type of these properties. So foo will start out as an empty object which has just a hidden class of, let's call it star. And then once we define x, we create actually a subtype in V8 Notion, which inherits from the star class, which we call x. And then we define foo. So now we have a type xy, which inherits from x. And this type hierarchy is representing our foo object now. And any optimizations done by node is based on this object. Once we create another object bar, we again start out with the star type, which we already have. But now we define y first and x later. And we end up with a different type. And this is not because the V8 engineers didn't oversee this problem. The problem is that detecting these similarities at runtime would cost you a lot of processing power, and you don't want to do that. So in JavaScript programs, you always also have to watch out in a way that you either have identical object definition site or that you have very similar objects, such that V8 has no problems detecting your type similarities. And this is simply a consequence of how computers work. And we don't like to think about how computers work nowadays. We like to write functional, untyped programs which don't really resemble the hardware anymore. And then it's up to the runtimes to optimize this code. But the general problem that this code still needs to fit a certain structure in a way in order to be easily optimized. This problem doesn't go away. And in my opinion, it's also a reason why for performance critical systems, type-safe languages typically are the better choice. It's just much more easy to retain such structure if it's explicitly in the source code and not only has to be figured out at runtime by the compiler. And it's like this also, like if you look at PHP actually in the early days, their virtual method tables were hash tables, and the hash function for the methods was the number of characters in the method name. That's one reason why PHP methods have so erratic names. It's because if they all have different name length, they can be better hashed and they're more performant. And that's of course quite an idiosyncrasy. But this is how programming languages evolve sometimes, and PHP started out like that. So I'm not sure if it's still done that way, but in a way, even in untyped programs like JavaScript programs and PHP programs, you have these constraints, and you can't really trick the hardware and to run fast without being explicit about your program. It's basically what I'm trying to say here. Simon, how much time do I have left, by the way? I haven't checked my watch, unfortunately.
So you have about 7 minutes or so.
7 minutes, okay.
Take some questions after that as well.
Perfect. Then I'm way beyond schedule. But that's okay. As I said, I'm rather doing this slowly, but you understand it. But and you can always find the slides. I also gave this time a couple of times. I'm always trying to cover different things. I'm just running through branch prediction, I think, and then we can take some questions. So branch prediction, what we do here is that we create an array of 20,000 elements with a random value. And then we run a program which 1,000 times computes the sum of this array, this very same array. What happens though, we don't really compute the actual sum. We want to add the number if it's bigger than 50, and we want to subtract the number if it's smaller than 50, smaller or equal to 50. So, and what we have here is a branch. A branch is a conditional control flow. And as a matter of fact, for the processor, it is important to know what execution comes now, or what sequence of execution comes next, because a processor has caches to preload values and to preload instructions. And if these caches aren't filled with the correct information, then the processor has to flush these caches, and basically it stalls until new instructions to execute arrive. And therefore, it's important that a program is predictable. And in this case, it's not, because we have random values between 0 and 100. So this is basically a 50-50 chance, more or less, whether we have to do the plus or the minus. And this is confusing the processor, or it's basically making it slower in the worst case. Doesn't necessarily hold for all processors, but for many it does. So how can we make this program faster? Well, we can, I have called here, we can add this array sort here. Because once we sort the array values from 0 to 100, we will, for the first couple of values, we will always subtract, and we will always increment after. And by this, we even though we added more work, since we do the adding so many times, we have generated a faster program. And it's basically the moral of the story is the same as with virtual method dispatches. If your program is very predictable for the compiler in the other case, then your program will run fast. If you have to guess what comes next, and you have a very short horizon of what instructions you have to execute in the near future, then your program will run slow. So it always pays off to basically run code that has to run many times, to run it in the most predictable manner possible, to give your runtime a chance to optimize it as much as it can. And this holds true for if-else statements the same way it holds true for virtual method dispatch. And it's not surprising, though, because both basically reduce to the same concept, right? They both, you can express an if-else statement with a virtual method dispatch. In Smalltalk, even if-else is implemented as a virtual method dispatch on Boolean object, which executes the one thing if the object is true and executes the other thing if the object is false. So those two are equivalent. And what holds for branches holds for virtual method dispatch. And this is basically the moral of today's talk that I hope you can take out of this. Once you look into performance problems on this level of algorithms, of batch jobs especially, try to avoid these sort of unpredictabilities and you will be good. So now I'll scroll through a couple of slides that I absolutely have no time of doing. So don't, escape analysis, that code elimination. So it's a bit of a shame. Please check. I don't know why it took so long today. It's maybe because I don't have an audience, so I can't see people nodding. So I repeat myself, but not fair enough. So yeah, also these things are important, but not topic of today's talk. Still, that's one last thing. Once you benchmark things, also be careful, because benchmarking tools not necessarily show you the actual performance of a program. And the problem is that benchmarking tools have some constraints. For example, they cannot run all of the time. Sometimes, let's say you have a program that is running in a running or in a blocked state, but your benchmarking tool is only ever allowed to be run by the VM when it is in the blocked state. So then the benchmarking tool will tell you that your program always is blocked, and this is of course not the result you want to look into. So since I'm through, if you're in Norway and watching this in Norway, I'm working at Sienta, which is my company here. So please check us out if you're interested in a job, or if you have a job for us. And other than that, I've been contracting for a performance monitoring tool for the last year. That's partly why I know these things. It's called Instana. It's an APM tool. We just started not so long ago, but the tool turned out really great. So please have a look at that one. Other than that, I'm Rafael, as I said in the beginning. You can find me on Twitter on Rafael Codes. I have 2 open source projects that I run myself, which are GitHub, ByteBuddy, and Documents for J. If you have some time, please check them. And as I said, JUX Innovation Awards, if you can give me a vote there, I very much appreciate it. And also for Mockito too, please check out the release candidates. We really would appreciate some more feedback than what we have so far. And yeah, thanks for joining me here in these 45 minutes where I didn't get through my slides. Sorry for that.
That's awesome. Thank you very much, Rafael.
Thanks.
And a couple of things then. We've got some questions. I actually did post the link to the JAX London voting for the JAX Awards in IRC. So please do check that out. Bike Buddy is an awesome tool, so definitely deserving of a JAX Award. Okay, a couple of questions. In fact, there was one which Martin answered. I think I'll probably mention it again, though, just in case others aren't aware. Let me find the question. The question was about which kind of profiler you can use to grab this kind of information. And Martin suggested JITWatch. Anything else you would recommend?
So JITWatch was actually in my slides. JITWatch is a great tool because it allows you to look into the machine code and also shows you the compilation stage you're in. So, but then you have to read machine code. But if you want to get the full picture, it's actually the best way. Other than that, JMH is like my standard tool set for any form of micro profiling. JMH is like a benchmarking framework made by a previous Oracle engineer who's now at Red Hat. But it's really the best tool out there. Because it basically tricks the compiler into just optimizing this piece of code that you want to measure. And it also, for Linux at least, I think Linux support was added very recently, you can do perf ASM profiler, which allows you to run the Linux perf command on the ASM. So you see the assembly plus the perf. So you can already see where your program spent the most time at. But again, you have to read some machine code. Even though, don't be scared of that. People tend to treat these performance questions with like, "Oh, only the big boys can do it," but it's nonsense. It's not that difficult in the end. It's just not so well documented, in my opinion. But in a way, for small programs, the machine code is pretty straightforward, but there's a lot of noise. So at least try it, and there's comments often in the assembly that will help you to identify, and otherwise just talk to people. There's like the performance user group. There's a lot of great places to find help.
Actually, that links nicely onto the next question, actually, from Sunnick, asking about a good place to go for information on this topic from someone coming from a zero knowledge kind of place. A couple actually that Martin's already mentioned. Mechanical Sympathy, which is the blog from Martin.
Yeah. Peter Lorre has a great blog. Mechanical Sympathy by Martin Thompson is a great source. There's a few high performance specialist people that really have excellent material. I guess they also have classes for these sort of things, but in the end, it's like getting your hands dirty a bit as well. Just try out benchmarking and then ask questions, and really ask questions, because otherwise you will not get anywhere.
And a great place to ask questions, actually, Martin also mentions Friends of JClarity, which is a great mailing list. It has a load of really top performance engineers on there as well. So that's a great place to ask questions as well. Okay, let me double check any other questions. Question for Rafael from Stefan. Doesn't the branch optimization directly in Java code make the program design less understandable?
Yeah, I mean, that's always a problem. There's this curve where you generally, if you write nice programs, the JIT will honor it, because the way that the Oracle engineers built the JIT is to say, okay, what is a good Java program and how can we optimize it? So if you do anything weird, it typically doesn't help you. But once you hit a certain level, you will need to interact directly with the JIT in a way that you try to trick the JIT into doing certain things. And that's especially with false sharing, something I didn't get through either. Typically, people like added empty fields in between two fields to avoid false sharing. Then you get to this level where you have to do ugly things to trick the compiler to do something particular. In the end, it's a trade-off what you want to do. Do you really need a fast program? Then you have no other choice. Otherwise, I always recommend to not do micro-optimization, because your program probably spends 60% doing JDBC calls anyway. So these 2 milliseconds you get out somewhere, that don't really matter for your program anyways.
Awesome. Any questions from the Melbourne JVM group?
You mentioned some of the logging frameworks can cause some performance issues with vtable. Are there any that you found pretty good in that respect?
It's not the logging frameworks that are open source typically. It's the logging frameworks people built for themselves because they don't like the API, for example. It's like the type of logging frameworks I see at my clients sometimes if they build themselves. Logging frameworks are actually they're all pretty good. in my opinion. Generally, you should still avoid logging. Like a lot of logging is also a typical thing that I see, which causes performance issues. What often can cause trouble if you do like synchronized loggings, like you write to a file synchronized with the logging. It's better like to append it to a thread local buffer and then fetch it from there, which like log4j2 is actually pretty good in that regards. But also, I mean, the classic ones, logbacks, they're not bad at all. But I would say, like, if I had to choose one today, I probably would go for log4j2.
Awesome. Any other questions from Melbourne? So I can hear you then, Con. Any questions?
No, no more questions from here.
We're all good. Awesome, yeah. Awesome. Okay, so let me just share my screen. So I'll say a massive thank you to Rafael. That was a really great session. Very interesting, and nice to get a deep session on VJug24 now. So we've broken our deep techie duck for good quality content. So that's amazing. Thank you very much, Rafael.
Thanks for having me.
Cheers. And our next session is going to be, let's double check what our next session is.